folks. Number 4 is very similar to your WebAssign problems. Second set. Calculate the amount of heat to raise temperature of this stuff to that temperature change. The specific heat capacity is given. The formula to use here is Q equals M times C times delta T. The M is given here, 292 grams. The C is given here, 2.42 grams per joules per gram per degree Celsius. 2.42 joules per gram per degree Celsius. And the delta T is the change in temperature. It's this minus that. 343 minus 273.2. I cannot do that in my head. 343 minus 270, what? 3.2. 69.8. Now, it's important for you to remember from, I think, our first module that a degree Celsius is the same as a degree Kelvin, except it's just moved over. So a delta T in Kelvin is going to be the same as a delta T in Celsius. The size of each degree Celsius is the same as the size of each Kelvin. That's what you must remember. The only difference between Kelvin and Celsius is that Kelvin is moved over by 273.15 degrees, but the size of each degree is the same. So the change in temperature is going to be the same whether you're using Kelvin or Celsius. I have put Celsius here because I want to show you that the grams will cancel, the Celsius will cancel, you're left with joules. Are they asking for joules? No, they're asking for kilojoules. So I will do this calculation and then I'll convert to kilojoules. So I got 292 times 2.42 times 69.8. I got 292 times 2.42 times 69.8, and I got this many joules, but what that means is 49 kilojoules. 49.323 kilojoules. Let's have a look at the significant figures. I've got 4 significant figures here, 3 here, 3 here. So the answer has to be in 3 significant figures. So that's 49.3. This is going to be 49.3 kilojoules. Is this going to be positive or negative? Let's check it out. Required. How much heat is required? It's going to be positive. So nothing is giving off heat in this case. We're putting in heat to that ethanol, that 292.0 grams of ethanol. That's how you do number 4. Number 5 is going to be quite the same thing, except we're using a calorimeter here. So let me show you how this goes. This is the mass, and the temperature rose by this much. So this is the delta T. We don't need to subtract. It's already subtracted for us. And I'm going to solve for the C. Okay. So it goes like this. Same equation. Q equals mc delta T. This time I have the delta T. I have the mass. I have the heat. The heat's going to be right here. And I need to solve for the C. So before I start, let me just fix this equation so I can be solving for the T automatically. Is there a way to do this without algebra? No, I don't think so. I think the best way to approach this problem is with the algebra in the following way. I want C. They're asking me for determine the heat capacity. That's the C. So I need to divide everything by m delta T so I can get C alone. So I get Q over m delta T equals C, because the m's cancel and the delta T's cancel. All right, now, I know the m, that was given, the delta T, that was given, but what is the Q? Here, let me give you some, give myself some room on top. So the Q is given right here, except for one thing. This is, oh, there's a typo in here. This should be kilojoules per, this should be kilojoules. Sorry about that. That needs to be kilojoules. All right, now This is for the kilojoules that you get from doing this reaction once. But I do not know how many times this reaction is actually happening, right? All it says is that some grams of this stuff right here, is combusted in the calorimeter. So if some grams of this stuff is combusted in the calorimeter, how many times is this reaction going? If this reaction just happens once, then yeah, it's negative 1.28 times 10 to the fourth kilojoules. But I kind of doubt that this reaction is happening just once. They give me this many grams that's reacting. Let me figure out how many grams, how many moles this is. Once I figure out how many moles this is, if it's 4 moles, if it's exactly 4 moles, then yeah, I can use this number directly. But if it's not 4 moles, I need to change this number to fit the number of moles of aniline that I'm actually reacting here. So, let's figure it out. They give me the molar mass, 93.13. So I've got 26.01 grams of aniline. I'll just say AN. And in 1 mole of aniline, I've got 93.13 grams of aniline. All right? The grams cancel, now I have moles. Now I know that for 4 moles of aniline, this is the energy that I get, folks. All right? So for 4 moles of aniline, why am I writing 4 moles in the bottom? Because I want to cancel moles of aniline. For 4 moles of aniline, I get this energy, negative 1.28 times 10 to the fourth kilojoules. Negative 1.28 times 10 to the fourth kilojoules. Okay, so now the answer is in kilojoules. That is going to be the Q. Okay, so this Q is going to be 26.01 divided by 93.13 times negative 1.28 times 10 to the fourth. I can't remember all that. 26.01 divided by, what was it again? 93.13 times, what was it again? Negative 1.28 times 10 to the fourth. Negative 1.28 times 10 to the fourth. So that's negative 3575 kilojoules. Look at the significant figures. There's only 3 there. So it's negative 3580 kilojoules. That came from negative 3575, rounded to 3 significant figures. That's the Q. All right, so now I have the Q. The mass was this, and the delta T was this. Right, so let's see if I can move this over. All right, so the Q was negative 3580 kilojoules, and the mass was 26.01 grams of aniline, and the delta T was 121.2 degrees Celsius. So, oh, that's J, by the way. I'll do this in a calculator, but then I'm going to convert this back to joules. 3580 over 2601 over 121.2. So 3580 over 26.01 over 121.2. That's 1.31. And that's 1.36 kilojoules per gram per degree Celsius. But I'm going to change this to joules, and you'll see why in a moment. So that's going to be 113. So that's, where's the mouse? Yeah. It's going to be 1136 joules. So this is 1136 joules per gram per degree Celsius. Notice I'm getting the units from here. This is joules, grams, degrees Celsius. I changed from kilojoules to joules on the fly by looking at the calculator and moving the dot over 3 times because the traditional units in chemistry for heat capacity is joules per gram per degree Celsius, not kilojoules per gram per degree Celsius. So that's why I changed this back down to joules. Now, let me draw you a picture so that you could understand conceptually what this type of problem is describing. It is describing, as it says, a bomb calorimeter. A bomb calorimeter is a device. It's usually solid metal, and there's some opening, some hollow space in the middle of it, where you do a chemical reaction. You could burn something. Usually, you burn something, and then the heat that is given off, it is absorbed by all this metal. The reason why we use metal is because, as you saw in problem number 3, metals have a very low heat capacity. So it's very easy to change the temperature of a metal. And there is a thermometer attached to this big piece of metal, and it measures the change in temperature. This is called a bomb calorimeter. There's a picture, I believe there's a picture of this in your textbook. This is chapter 5, of course. The bomb calorimeter's purpose is to measure how much energy gets lost in a chemical reaction, or absorbed. Usually it's lost. And it does that in the way that I've drawn. So because this experiment, or this problem, supposedly happened in a bomb calorimeter, the temperature change is not the temperature change of the stuff in here. It's the temperature change of the metal bomb calorimeter, okay? It's a lot of metal here, so that temperature change got measured, and it is you can calculate the heat of the chemical reaction by using that temperature change, that measurement right here. Now in this case, we already knew what the heat of the chemical reaction was supposed to be by the calculation that I showed underneath here, and we had to calculate the specific heat capacity of the bomb calorimeter. So remember, the temperature change was measured by the bomb calorimeter. So how much energy does that mean? It means it's the energy that it takes to raise the temperature of the bomb calorimeter by a certain number of degrees Celsius. So the heat capacity that I calculated right here for you is the heat capacity of the bomb calorimeter. That's what's going on in this problem. Usually, you would calculate the heat capacity of some substance, as we did, or as we used in number 3, that there were some heat capacities with substance, and then also in number 4, we used the heat capacity of some substance in order to calculate the heat that got released. No, the heat that was required to raise the temperature of some substance. But in this case, we're not using the heat capacity of some substance. We're calculating the heat capacity of the tool, right, of the bomb calorimeter, because this is the thing whose temperature gets increased by some reaction that releases heat, or some exothermic reaction inside of it. That's it for number 5. I'm going to stop this video now, and I'll do the number 6 in the next one.